Welcome to Measurement Study of a Process, Lesson 4. In Lesson 3, we looked at statistical process control and why it is used. We also looked at standard deviation, sigma, how it is calculated and why it is needed. We looked at capability index, CP, and how we can use it to determine how well a process is controlled. In this lesson, we will look at how a process control chart is plotted. In Lesson 3, we learned that capability is a measure of the ability of a process to meet specified requirements, usually expressed as an index CP. We saw the formula CP equals tolerance divided by 6 sigma. So what is the importance of 6 sigma? The next slide shows the spread of sigma within normal distribution. Here we can see the spread of sigma within a normal distribution curve, not taking account of tolerance. The ratio of tolerance divided by 6 sigma is the capability index. Here we can see 99.73% of values lie within plus or minus 3 sigma, which is 6 sigma, for normal distribution. Process control charts show how well a process is operating. Poor control can come from change in material, tool wear, or other errors. A process is said to be operating in statistical control when the only source of variation is down to common causes which are predictable and characteristic of the process. An X bar and R chart is a chart often used, developed from measurements of a particular characteristic of the process. Data is recorded in small subgroups, usually 5 pieces, taken at regular intervals. This is added to the chart so that X bar and range R can be calculated. The X bar and R values are then plotted. Control limits can then be calculated using constants and plotted. Analysis can then be made to see if the process from which the data was obtained is capable. Sigma calculations. Sigma is equal to the mean average of the range divided by D2, where D2 is a constant depending upon the sample size. So sigma is equal to R bar divided by 2.326, that particular constant D2. Constants are found on X bar and R charts. The use of constants in control charts enables the person who is constructing the chart to make much quicker calculations. The constants give a result approximate to a full, lengthy calculation and enable values to be plotted on a chart. The next few slides show the different chart areas and how the above steps are carried out. This is what the empty X bar and R chart looks like. Don't worry that it's rather small, as the next few slides will elaborate on some of the areas of the chart. Characteristics. This part of the chart shows the characteristic, what we are measuring, and the sampling frequency, how many, how often. This part of the chart shows records of the subgroups, 5 parts, x1 to x5. This part shows the sum of x, x bar and range R. Scales are chosen for R and x bar. X bar and R data can now be plotted. R bar, the average of the range values, can be calculated and plotted. In this case, R bar equals 0.023. The upper control limit for range, UCLR, is calculated from R bar, which we know as 0.023, times another constant, D4, which is 2.114. This gives an upper control limit range of equal to 0.0486. The upper control limit for x bar is calculated using the mean of all x bars plus constant A2, which is 0.577, multiplied by R bar. So for this particular graph, we can see that's equal to 3.07 plus 0.577 times 0.023, which is equal to 3.07 plus 0.0132, and that gives us an upper control limit for x bar of 3.0832. Note that the mean average of all x bars is pronounced x bar bar, drawn like this, an X with 2 lines written above it. The lower control limit for x bar is calculated using the mean of all x bars minus the constant A2, which we know as 0.577, multiplied by R bar. That's equal to 3.07 minus 0.577 times 0.023, which is equal to 3.07 minus 0.0132, and that gives us a lower control limit for x bar as being equal to 3.0568. You may have noticed that there are points beyond the control limits which we have previously calculated. The presence of one or more points beyond either control limit is evidence of non-control at that point. Since points beyond control limits would be rare if only variation from common causes were present, we predict that a special cause has accounted for the extreme value. Therefore, any point beyond a control limit is a signal for immediate analysis of the operation. Points above control limits suggest the control limit or plot point has been miscalculated, the piece-to-piece variability or spread has worsened, or the measurement system has changed, for example, a different inspector or gauge. Points below control limits suggest the control limit or plot point are in error, the spread has worsened or even improved, the measurement system has changed, including editing or alteration of the data. Patterns or trends within the control limits. The presence of unusual patterns or trends can be evidence of change in process spread. This could give the first warning of problems which should be corrected even before points are seen beyond the control limits. Certain patterns could be favourable and should be studied for possible improvement of the process. A run above the average range or a run up signifies greater spread in output values, a shift in a process element, for example less uniform material, or the measurement system has changed, for example a different worker or gauge. A run below the average range or a run down signifies a smaller spread in output values, which is a good condition that should be studied. A change in the measurement system, which could mask real performance changes. Once there is enough data, usually 30 to 50 samples, then the control limits for X bar and the average range can be calculated. Further data can be added to the chart, but the control limits should only be recalculated when a deliberate process change or a process improvement is introduced. As we have already learned, capability is a measure of the ability of a process to meet specified requirements, usually expressed as an index, CP. Process capability measurement can be made using the data that is obtained for the control chart. The capability measurement compares the process spread with the specified requirements. There are two types of process capability study: initial or preliminary process capability study and an ongoing process capability study. An initial process capability study is conducted to obtain early information on a new or revised process. An ongoing process capability study uses data from a longer time period to include all common causes of process variation. Both studies use control charts. Process capability measures how well a process is generating a specific characteristic with respect to specification limits. Indices used are PPK for preliminary process capability studies and CPK for ongoing process capability studies. Process capability assesses the process spread with respect to the width of the specification. It assesses the process average with respect to the specification, and it depends upon the process location and spread. Here we can see process indices and their descriptions. PP is equal to preliminary process potential. PPK is equal to preliminary process capability. CP is equal to ongoing process potential, and CPK is equal to ongoing process capability. Here we can see some calculations for our process indices. PP and CP is equal to the specified tolerance divided by the process spread, which is equal to the specified tolerance divided by 6 sigma. However, PPK or CPK is equal to the minimum of the upper specified limit minus X bar bar divided by 3 sigma, or X bar bar minus the lower specified limit divided by 3 sigma. These are found on X bar and R charts. There are some guidelines for process indices. PP should be greater than 1.67, as so should PPK. CP and CPK should be greater than 1.33. Note that these values are guidelines. Customer requirements may differ from these values quoted. Let's go right back to the data of our bores for a moment. The data that we saw for the bore diameter showed that 2 parts were out of tolerance. If this was data from an ongoing process study, would we expect a good value for CP? Would we expect a good value for CPK? Discuss this in your class. Let's look at the bore diameter and the characteristics. This part of the chart shows the characteristic, the bore size, and the sampling frequency, 5 per hour. This part of the chart shows records of the subgroups, 5 parts. Note that the bore size diameter has been recorded every hour. This part shows sum of X, average X bar, and range R. Scales are chosen for R and X bar. Range data is plotted with UCLR being equal to 0.0655 and R bar equal to 0.031. Upper and lower control limits for X bar are calculated and plotted, and X bar bar line is plotted. Here, values for CP and CPK have been calculated. So CP is equal to 1.2505. Note the value for CPK is the lesser of 1.9759 and 0.5252. So CPK is equal to 0.5252. From our bore diameter data, we already know that 2 items of data were outside of the tolerance. The value for CP was 1.2505. This is below the guideline expected, 1.33. It is different from the value we calculated, 1.185, as the chart uses a constant, so gives an approximation to the calculated value. The value for CPK of 0.5252 shows that our process is not capable, as the guideline is 1.33. This should not surprise us, as although the data showed a normal distribution, this was not spread about the nominal size. The requirement for our bore diameter is 36.32 plus or minus 0.05 millimeters, so the bell curve has a shifted location to between nominal and top tolerance. Tolerance limits are a consideration when calculating CPK. This is only a hypothetical situation. The operator should stop and investigate the process if parts were measured and found to be out of specification. This will be recorded in the comments area of the X bar and R chart, which would offer help when analysing the trend lines for range and X bar. We have now learned that an investigation into defective parts can involve quite a lot of mathematics, including statistics and the plotting of statistical process control charts. We have seen just one type of statistical process control chart. There are many more. It is the analysis of those charts that can help us understand problems in manufacturing and how to overcome them. I hope that these lessons have helped you understand that problems do occur, and that when they do, we need to take action based on information to correct the problem and stop it happening again.